So back with part 2 then of the sample assessment material for the higher year 10 triple paper. So we've got a little bit of information about solar cells there, and we've got a prediction which we're going to use later. The first task that we need to do is to calculate the mean. Now we've got to go to the same degree of accuracy. We can't put, so 18 plus 17 is 17.5, but we can't put 17.5 because the level of accuracy is to, well, there's no decimal place, so we need to just round that up to 18. So that's your first mark. So if you put 17.5, you won't get the mark. So always check the degree of accuracy. Which is the least repeatable. So that means with the biggest range. So when we look at the biggest range here, we've got 19 and 25. That's got the biggest range. All the rest of the sheets are pretty close to each other. Given that we're not expected to remember this, or it's not at the front, but we're just given this uncertainty equation, and we're going to do this for 3 sheets. So I'm going to look at the biggest value and the smallest value. Okay, so when we look at the 3 sheets, biggest value, smallest value. Actually, it's just the trials, isn't it? I think, yeah, trial 1 and trial 2, and divide that by 2. We come up with 2 milliamps. Okay, we just keep it in the same degree. 6 groups compare. Why? We're going to see if their data is reproducible, and if it is, we can get more confidence in the results. So the big difference between repeatable and reproducible: reproducible is when other groups come out with similar results. Repeatable is when you yourself or your group come out with similar results. It's a bit of a pain, this one, because this is going to land up on a different page no matter what. So the results are there and you have to plot them there. So you're going to get, is it 4? It's only worth 3 marks. Usually 4 marks if you have to put your own scale in. But I guess because it's an easy scale, they're only giving a mark for the scale, a mark for plotting, and a mark for the curve. So you've got 3 marks available there. Using information from the graph for 3 marks, and you can see where I was doing that. Discuss the student's prediction. Well, if we go back to this, they're going back 4 pages now. They think that it's going to be inversely proportional. So inversely proportional, the line would kind of look like this, but it would be a straight line. Okay, this is curved, so I know for a fact it's not going to be inversely proportional. It is inverse because as one gets bigger, the other one decreases or gets less. But I'm just going to take 2 values here. I'm going to take 3 and 6. So if you double 3, you get 6, and I'm going to just take the mean current. And you can see already that if I double the one, I'm not going to half the other or double the other. These I can show there. So 3 sheets 48 milliamps, 6 sheets 28. So I've just said they're not inversely proportional there. In practice, the money saved is not always the same because we're going to link it now to cloud cover each day for solar panels. You're not going to always get the same amount of sun, so the amount of energy produced will be variable. Okay, so that's that question there. On to question 6 then. So this is a 1-page question on pressure. So we've got a little bit of blurb saying for safety reasons cans must be able to withstand 620 kilopascals. So that's times 10 to the power 3 there. We got a can being thrown into a bonfire, which I wouldn't recommend doing. It starts from 27 degrees Celsius and it's heated to 227 degrees Celsius for when it's thrown into the bonfire. So first of all, we need to just use the model of molecular motion to explain how the pressure is going to be inside that can. And I've said molecules will gain kinetic energy as the temperature increases, so there will be more collisions per second on the wall of the can and with each other. And then we've got the 4 marks there for using this from your front page. So it's PVT equals a constant. We don't use a volume, so we can get rid of the volume. So now it's just P1 over T1 equals P2 over T2. I'm given two temperatures, and I'm asked to find the pressure to see if it will be greater or less than 620 kilopascals. So let's do that. So first of all, I need to convert the temperature into kelvins, and to do that, again, at the front of your book is plus 273 for each one. When I do that, I'm going to take my my pressure there of the can, which is, because it's a kilopascal, it's times 10 to the power 3. And I'm going to put that over my temperature in kelvins, and then I simply rearrange for my pressure. And my pressure comes out to be 4.7 times 10 to the power 5, which is 470 kilopascals. So it doesn't explode. Okay? Now looking at this, I just realized I'm converting from kilopascals into pascals, and then converting back into kilopascals. So I wonder, I haven't tried it, I haven't got time to try it, but I wonder if you didn't convert this, whether you probably would, thinking about it, you just come up with 470 there, if you didn't convert, because it's in kilopascals anyway. So I've probably done an extra step I didn't need to do there. Okay, on to question 7 then. So this question is on kinetic theory, and you're given some specific heat capacities there, and we're asked to define what heat capacity is. So it takes this amount of energy to heat 1 kilogram of aluminium by 1 degree Celsius. So we need to know specific heat capacity definition. We also need to know the latent heat ones as well, the one for evaporation and the one for I can't remember the other one. I think it's melting. But then we come on to an equation for 2 marks, which is a fairly simple equation. So this is the only one, the equation that links with specific heat capacity. So we're given a mass, we're given a specific heat capacity, which is, you see, for aluminium, and then we're given a temperature change, which is from 20 to 80, so that's going to be 60 there. And we come up with 39,600 joules. And then we come to a 5-mark question, quite a bit involved here, and I should have color-coded this a bit more, maybe. So what we're doing, we're taking this block now that's been heated from 20 to 80, and we're going to put it in some water. And we need to see the temperature change of the water, I think, calculate the original temperature of the water. So we know that the block was 80 degrees to start with, and now when we put it in, it's 30.5. The mass of the water in the beaker is 0.5, so we can use that. So first of all, let's see how much the aluminium dropped. So it dropped from 80 to 35. So that's see how much energy was involved there. Well, I'm going to use the same equation now, and you can see that I've taken that away. So I got 49.5 degrees Celsius change. So I'm going to use the same mass, 0.75. I'm going to use the same specific heat capacity, and I'm just going to put that new temperature change in, which comes out to 32670 joules. And I'm going to do the same with water now, but obviously I don't know that other temperature. That's what I'm solving for, but I do know a bunch of other stuff. I do know the energy that's gone in. So what I can say is 0.5, which is your mass, times my specific heat capacity of water, which is this one, which I should have highlighted really, times my temperature change. Well, I know my starting temperature is that, but I don't know my other temperature. Or what I should say is, yeah, my final temperature, or the original temperature, I should say. But I don't know it equals this amount of energy, because that's how much energy this aluminium took to heat, or to not heat by 1 degree Celsius, 1 kilogram of it. So we can use that and rearrange, and that's all I'm doing here is I've halved this, 0.5 times that. So I'm just simplifying through now, simplifying through all this until I get T on this side, which equals 15.6 minus 30. So it comes out with a minus figure, which tells you that it is a decrease in temperature there, 14.9. That was its original temperature. So then when you put the block in, which was hot, it's going to raise that temperature from 14.9 to 30.5. So quite a tough question there for 5 marks. But yeah, a lot of rearranging with that. That's where your marks are, and understanding what's happening. And then explain which of oil or water is better coolant for the car radiator. well, we can see that water's got a higher specific heat capacity, which means it'll take more energy to heat it by 1 degree Celsius. So you can say something along the lines of they both reach the same temperature in the engine, but water has a higher specific heat capacity, so will absorb more per given mass. So the water is the best one for the coolant. And it comes as brings us on to the last question then, question 8, which is a stinking question. So I'm going to try and explain this the best I can. There's a couple of figures here. So we've got this amount of plastic bottles are used each day, but only 45% are recycled. So that's the one thing. So of all the bottles that's used in Wales each day, only 45% are recycled. Now, the mean volume, one crushed plastic bottle, the mean volume is 50 centimetres. But we get them, and they're all crushed into a bale of a mass of 190 kilograms. Okay, so that's all fine. And I think this bit's for the next question anyway. Okay, so plastic has a density of this. How many bottles are produced each week? So we're going to have to use the density equation, because we're given density, we're given a mass. Well, we're not given a mass yet, because we have to find out the mass of each bottle. But we do know the mass of a bale. And we know the volume of a crushed bottle there. So that's what I'm going to use. I'm going to use the density and the volume first. So I'm going to use that density times, so this is just a rearrangement now of the density equation. So mass now is going to equal the density times the volume. So I'm going to use the density times that volume of each bottle. And that gives me a mass of 47.5 grams per bottle. Right, now that I know that, I can put that now, because I know each bale is 190. So let's find out how many bottles are in each bale. So to do that, I see how many times each bottle goes into that. So the mass of each bottle goes into the mass of the bale. So I got 4,000 bottles. Now, it told us that of this amount of bottles, only 45% are actually recycled. So let's work that out now. So I've got 45% is 45 over 100. Okay, they kind of teach you that in math. Times my amount of bottles that's recycled, and that's per day, so I need to times that now by 7, because there's 7 days in a week. I come out with 2.28 times 10 to the power 6. Okay, so that's how many bottles are recycled each week. Therefore, I can now get my 4,000 bottles that's in a bale and see how many times that goes in to how many this recycled per week, and then I come up with 570 bales. That is a really tough question for 6 marks. Okay, a really tough numeracy question there that is hard to pick out, but that's the way it's done. Okay, so if you have to rewind and listen to me run through that again, please do. And if you need to come and see me about this, come and see me, and then we can move on to this question now. And again, this is still a difficult question. We're going to use pressure now equals force over area. And from this blurb here, it says that y is 15 times bigger. So again, it's another numeracy question. And it also said that it equals, where is it? It says somewhere there, the pressure applied position is the same as pressure exerted at x. So I know if I'm solving for one of these, which I am going to be, that the force at x over the area at x is going to be equal to the force in y over the area in y, because they're equal pressures. Okay? So knowing that y is 15 times bigger than x, this is where I've got this relationship from. So the area at x, okay, if it's 1, then the area at y is 15 times bigger. That's what it tells me there. And I'm also given a force at x, which is 500. So if we look there, the force at x is 500. I know this area, is 15 times bigger than this. So if this was 1, this would be 15. And now I can rearrange to solve for the force at y. So So when I rearrange, it's going to be 500 times 15, which is 7,500 newtons. So again, not a very nice question there. Explain why air bubbles in the hydraulic liquid make the press less effective. It's because air/gas can be compressed, so a larger force will be needed to exert at X to exert the same force at Y. And that is the end of the paper. So I hope you've got something from that. It was a bit of a stinking last question, but doable if we look out for the right things. Thanks for watching.